Feature Purification, How Adversarial Training Performs Robust Deep Learning. This is a joint work with Yuanzhi. So nowadays, we have very powerful deep learning models that can, for instance, tell us cat images are cats. But today, let me ask a very fundamental question here. That is, what are the features in those intermediate layers? Some of you may say, well, we sort of know that, right? The first layer or the lower level neurons are maybe learning the so-called edge and color features. And as you go deeper and deeper, you learn things that are more and more complex functions over the previous layers. And in particular, if you Google for the latest effort on feature visualization, you will see very pretty images like this. They seem to agree with what we think, that as features should get more and more complex as layers go deeper and so on. But today, let me really challenge this by telling you that this picture may not reflect what the features really are. So think about it. If you want to visualize, say, the neuron here, here is the most natural thing that you want to do. That is, you start from a uniformly random image here, say like 0, 1, uniform between 0 and 1 per pixel. Then you try to take the gradient of this neuron with respect to the input. And then you move in the direction of that gradient. You take the gradient again, you move, and they say that you alternate for like 100 steps. In this way, you can get a resulting image that, at least to some extent, maximally excites this underlying neuron. So this is the way that we think one should visualize the neuron, right? But in practice, what people do is actually to add a lot of tricks on top of this to make it more and more like real-life images. So this is known as like strong regularization. For instance, they try to reduce the components of the input images in the higher Fourier frequency directions. They try to reduce that to make it more like real-life images. But if you ask me, like, suppose we just remove all of those regularizations and just do the purest version of feature visualization, then what do we get? I claim that you're going to see very crappy features, okay? So it says like nearly for every single layer of, say, white ResNet, the neurons are actually learning something that look like noise. This may be surprising to some of you if you are seeing this for the first time, but I claim that you should not be surprised because this is very strongly related to something known as adversarial perturbations. Namely, suppose we're given a very well-trained image classifier that tells us, say, pig images are pigs with 91% of confidence, super high confidence. Then I claim that for almost any such classifier, for almost any image both in the training and the testing set, even though the classifier is so certain that this is a pig, but there always exists some perturbed directions that you can construct, which only changes each pixel by, for instance, 0.5%. And then the resulting image can completely fool the classifier to make it just say anything. Okay? And the fundamental reason for why such adversarial directions to exist, if you think about it, is precisely because the neurons are not learning what we want them to learn. They're learning something that looks like noise. For such reason, if you perturb a true image in the direction of the noise direction sitting on this slide, then it's going to change the output of the neural network. Okay? So let's now be a bit more concrete to make sure everyone's on the same page. If you take your favorite like image classification data set and suppose you use like a convolutional neural network like ResNet to do the training, it's very easy to get, say, more than 94% of accuracy. And as I said, if you perturb like each input image just by 0.5% per pixel, you can just make the accuracy to drop to 0. And one thing I haven't told you is how to construct this perturbed direction. It's actually simple. You just take the gradient of the loss function with respect to the input image, and then you like move for like 7 steps, and that can help you basically get a new image that will, but with a very different classification result. So this is how to construct the adversarial examples. And then this is bad, right? It means like if you spend a lot of time on the clean training, then the model is not robust against even just a tiny bit of perturbation. So how do we fix this? 5 years ago, Madry and others in his group proposed a very clean and very interesting simple method that they call adversarial training. It does the following. That is, it says during training, let's not use the true images or the so-called clean images. Let's use the perturbed images as training data. And then you train your model just like you did it before. And they notice that the resulting model actually becomes very, very robust, at least like against the, such adversarial perturbations. So therefore, like two natural questions arise. Number one, why do adversarial examples exist after clean training? And number two, how can adversarial training actually remove those adversarial examples? So in this paper, in this joint work with Yuanzhi, we actually use mathematical theorems to tackle both problems at once. So our main theorem can actually be stated in a conceptual way without any math. Namely, we show that during adversarial training, the neural network will not learn new features and will not remove existing features. What it does during this process of adversarial training is actually to purify a small part of each learned feature. So let me show you a picture to see what this means. If you take, say, the first layer of like a convolutional neural network, and if you do clean training, as we recall, like you learn edge color features. But now if we just start from a model that is clean trained, and we continue from there to do adversarial training, I claim that the features on this first layer are not going to change by a lot. You see that there's no new feature, and also the features are not really removed. So what happened to the features is that they get purified. Say this used to be like 2 colors, but now it's 1 color. This used to be like 3 stripes, it becomes like 1 stripe, and so on. So basically, without me even defining any math, I think you can convince yourself that the features of the first layer during this process of adversarial training get purified. And this is not only true for the first layer, it's actually true for every single later layer. For instance, layer 13, you can also see this feature purification process happening. And in fact, because every layer gets purified, then little by little, the cascading effect can be huge. As a result, remember that I showed a few slides ago that if you just do clean training, the neurons are not learning something meaningful, like they're learning something that looks like random noise. But now, if you start from there to do adversarial training, I claim that the cascading effect can be huge. In particular, the neurons really learn what we want them to learn. For instance, you see like this is a horse, this is like a truck, this is a car, and so on. Okay, so this is like a kind of proof by picture that that I hope that convinces you that what adversarial training is doing in practice is to purify the learned features layer by layer. So in the remainder of the talk, let me show you actually a little math to see why this happens. Okay. In particular, I'm going to make assumptions on the input distribution, and suppose the inputs are vectors satisfying a sparse coding model, namely like the x equals to some dictionary matrix times a sparse decoding vector plus noise. So the sparse coding model makes sense because many real-life data sets are indeed sparse in some bases. And here, like in particular, I want to make some concrete assumptions here. So for simplicity, let's think about the dictionary matrix being unitary and square. Okay, so we support like non-square, rectangular, and incoherent matrix, but for now, think about it being unitary, so the columns are orthogonal. And also, we are going to assume that the decoding vector z is a random k-sparse vector. Okay. In particular, we normalize it so that its L2 norm is roughly 1. So per coordinate is 1 over root d roughly. And each coordinate of zi is either 0 if it doesn't exist, or if it exists, it's at least like 1 over root d, between 1 over root d and 1. Okay. So in our actual paper, like we don't need this strong assumption. As long as there is a gap between the signal coordinates of z versus the non-signal coordinate of z, as long as there's a gap between the two, then that's okay. But here, for the simplicity of the talk, let's think about the non-signal coordinates just be completely 0, and we have only like roughly k of those like non-zero coordinates. So that's the randomness of this decoding vector. And let's think about k being something like d to the 0.35. So in particular, the smaller k is, then if k is too small, then we don't get a separation between the clean and adversarial training. And if k is too large, then the training just becomes impossible, and so on. So we want k to be something like, say, between d to the 1/3 and d to the 1/2. Okay, and here Cauchy is some noise, and suppose the Cauchy just satisfies a Gaussian distribution with a norm that can be as large as 1,000. And finally, let's consider a binary classification problem in which the label of this classification is just the sign of some ground truth vector W star times the decoding vector. So think about W star just being 1, 1, 1, 1. Okay, so this is the data distribution we're going to take. And to begin with, let me first show you that this seemingly like linear classifiable data, why linear models do not work on it. Okay, so let's think about linear model first to tackle this distribution. So recall that the label is a linear function, but it's on the decoding vector z. It's not on x, but it's on the decoding vector z. So therefore, the most natural linear classifier one should construct is the following. That is to take the m transpose times w star then times the input x. So this function actually, its main signal part is precisely what we want, but it also has some noise sitting on top of it. So now let me claim that the linear classifier is bad for at least 2 reasons. Number one, if we have a large Gaussian noise, then this noise part can be, as large as say 1,000, then they can just dominate the main signal part. So that's one reason the linear classifier is bad. But even if you don't have Gaussian noise, I claim that it's also bad against L2 perturbation, even just by a very small radius, like 1/√d. And this is easy to see because if you perturb the input in that direction of the predictor, just by, for instance, -10/√d, then you can change the signal by a magnitude of 10, so that can also flip the sign of the main signal and so on. So therefore, like linear classifiers for our data distribution is bad for 2 reasons, both against the Gaussian noise and against the L2 perturbations. Let me now, in contrast, construct a 2-layer neural network that will be actually robust against both Gaussian noise and L2 perturbations. For simplicity of the talk, let me just show why it is robust against L2 perturbation. Okay. So here's the construction. For each column of the dictionary matrix, for each dictionary word here, I construct 2 neurons, one in the positive direction of that, and the other one in the negative direction of that, with some bias term. Okay, and using the ReLU activation. So here's the bias. If you take it to be 1/√2 times k, then this function, you can approximate it just by the thing above, with an indicator function of the times like the linear part. Okay, so just believe me, this is true. And now let me try to convince you that why this function is robust against a very large L2 perturbation, in particular an L2 perturbation of radius 1/√k, which is much larger than 1/√d. Let me convince you why this is true. Okay, so if we look at this quantity like mi times x, if you don't have noise, then this is nothing but the ith coordinate of z, right? Remember, like z is a sparse vector, so it's either 0 or that coordinate is at least larger than some threshold. So in our paper, actually, remember, like we only need a gap between the two, but for this talk, think about it being either 0 or larger than 1/√k. So that means this value is either 0 or 1/√k to begin with. And therefore, if you perturb it by a radius that's slightly smaller than 1/√k, then this indicator function is not going to change. If originally it's above the threshold, after perturbation it's still above the threshold, and vice versa. So this means the indicator function is robust against L2 perturbation of a very large radius. And as a result, recall that this indicator function is only on for at most k coordinates because of the input sparsity. Then this summation in the very end is only effectively adding k things together instead of d things together, right? In contrast, if you use a linear model, you can also write it up as a sum but of d things. But here is a summation of k things. And this just makes the function 1 order of magnitude more robust comparing to a linear classifier. Okay, so the takeaway message on this page is that sometimes using high complexity networks like the ones with ReLU is actually a bless. It can be make the model more robust than simpler models like linear models. But of course, wait a sec, I only showed you there exists a two-layer neural network that is robust. I haven't told you like why neural network training cannot find it. Remember, like if you do clean training, you're not going to get a robust model. You're going to get something bad. And why doesn't clean training find this constructed solution? Why not? Okay, let me show you on the next slide. So what actually happens that during clean training is that one can prove, although very non-trivially, that up to permutations and up to duplications. So first of all, the neurons of a two-layer neural network with ReLU activation will indeed learn those dictionary words. So without loss of generality, say that the first neuron learns the first dictionary word and the second learns the second, and so on. But on top of that, they not only learn that pure direction, each neuron also learns a dense mixture direction that correlates basically with every column of the dictionary matrix. So this is a dense direction on top of the pure direction. So this dense mixture on one hand is so small that it does not affect clean accuracy. But on the other hand, they are correlated with each other so that if you perturb the input in this common direction, it can change the output of every single neuron. And this is why and therefore like having those dense mixtures will necessarily make the model non-robust, for instance, against an L2 radius of 1 over root k. Okay. And now, of course, when we ask like, why do dense mixtures show up? So one way to prove it is to just write down the math and convince yourself that indeed this dense mixture will be accumulated step by step by SGD. So this is how we proved in the paper. But today, actually, let me show you the conceptual reason for why this happens without going to the math. Namely, if you look at this dense mixture, then up to those constants sitting in the front, so those dense directions are actually meaningful, like they correspond to this linear predictor direction that I showed you a few slides ago. So we know that linear predictors are not good, for instance, when there are Gaussian noise that are present in the data, right? And therefore, like if you train a neural network, it's not going to learn this linear function. But because neural networks are trained by local algorithms, such as SGD, so locally speaking, when the network has already learned those pure features to some extent, then starting from there to make an incremental progress, SGD does not need to continue to go in this pure direction. Actually, locally speaking, it suffices to move in a linear predictor direction to make continued progress. And that's why like this dense mixture directions keeps getting added to each neuron, and it shall not be removed even if like you have infinitely many of data. Like during the training, then they would just be there. So the final point I want to make is that if you use adversarial training, then because adversarial training use perturbed inputs are the ones that shall add those dense mixtures into them. And therefore, if you do adversarial training, it encourages the model to remove those dense directions. And that's why like the model becomes robust in the end. So to sum up, today I showed you a first separation result on a neural network with non-trivial activations between clean training and adversarial training. But in fact, let's zoom out a bit to take a more global look. I claim that on one hand, we have very successful applications of deep learning, but on the other hand, our theory is lagging behind. So maybe we cannot hope for proving why AlphaGo works, but I claim that we should at least shoot for something that matches what happens in practical deep learning. So here's what do I mean here. As theoreticians, we love to play with like simpler models and assumptions and so on, but we have to be very careful and selective. There actually exist other regimes in which you can prove that why adversarial examples exist and so on, but many of those regimes do not match what happened in practical deep learning. Today we are lucky that by studying like how features are learned, we at least found out a way that really matches what the experiments tell us. So this is actually a good start in which our us like theoreticians can start to influence practitioners. For instance, today, like I showed you that the difference between clean features and robust features are so small, and in particular, like it's even a common direction across different neurons. So this means if you have a clean model, one thing you can do is to make a low rank update and to only train that low rank part to make it robust. And we found out that it works very well in practice. And we even applied this to natural language processing data sets like to transformers. And with my colleagues at Microsoft, we applied it to GPT-3 and it works very well. So thank you. So I hope you like the talk.